All right, let's talk about the property of equality for logarithmic functions and solving equations. This is the last topic that we need to cover in this section, okay? So this is very similar to the property of equality for exponentials. If we have two logarithms set equal to each other and they have the same base, that can only be true if the interior pieces, x1 and x2, are equal to each other, okay? And this first sentence is just reminding us that the base has to be greater than 0 and the base cannot equal 1, just to formally go along with the definition of a logarithm. Okay, so we're going to solve each equation, then we need to check for extraneous solutions. Now, how do we check for extraneous solutions? What are the things that we're not allowed to have? Now, the bases are more or less going to be provided to us, so that's not going to be an issue, but the inside of a logarithm, think back to the function, the domain was from 0 to infinity. So to check for extraneous solutions, that means that we need to make sure the inside is positive when we plug our answer in, okay? It's all about, is this inside expression going to come out to a positive? That has to happen, okay? So for problem number 14, we have log base 7 of 2x plus 3 is equal to log base 7 of 8. And because of the property of equality, and because these are the same base, we get to say that the insides must be equal to each other. So we really just need to say, well, 2x plus 3 has to equal 8, otherwise this can't possibly be a true statement. So subtract 3 from both sides, and you get 2x is equal to 5. So you get x equals 5 halves. Okay? And we again want to make sure that that just doesn't give us a negative here. But if I do 2 times 5 halves, I get 5. 5 plus 3 is 8. 8's a positive, and 8 is the number on the inside. So this one's pretty quick and easy. It's just a matter of recognizing that because they have the same base, and we have a logarithm equal to a logarithm, the interior pieces, the 2x plus 3 and the 8, are equal to each other. All right? So we're going to work through a few different examples that are going to get progressively harder. Here we go. So for problem number 14, I'm sorry, not number 14, we just did number 14. For problem number 15, we have log base 5 of 14 minus x is equal to, hold on, I need a little bit more space here, misjudged. Let's clean this up anyways, we're going to need the board space, I'm sure. Is equal to log base 5 of x squared plus 4x. Okay, so again, we have two logarithms, they're both base 5, so the interior pieces must be equal to each other. So we're going to have the inside, 14 minus x, must be equal to the other inside, x squared plus 4x. Okay, so now we need to figure out how we're going to solve that equation. And I see an x squared, so it tells me this is quadratic, so the best way to do it is to set it equal to 0 and try to solve by either factoring or quadratic formula. So I'm going to move these two pieces off to the right, so I'm going to have 0 equals x squared, add the x over, plus 5x, subtract the 14, and this is something that's factorable because there are factors of negative 14 that add up to 5. So I get x plus 7 and x minus 2. So that gives me two results. X equals negative 7, x equals positive 2. The question is, can I keep both of them? And remember, the check here is just to make sure that the inside pieces will come out to positive values. Okay, so let's plug in negative 7. If I do 14 minus negative 7, I get 21, so that's fine. Okay, but let's also plug it in over here and make sure that works out. So when I plug negative 7 into this, I'm going to get 49 and then minus 28, which is also equal to 21. So that checks out. So negative 7 is in fact a solution to this equation. Let's try plugging in 2. Okay, 14 minus 2, that's 12. So that's a positive number. Plug in 2 over here, and we're going to get 4 plus 8, which is also 12. So it checks out. So both of these are in fact solutions. So this logarithmic equation has two solutions, negative 7 and positive 2. All right, 2 down, 4 more to go. For problem number 16, we have log base 3 of 7 minus x squared is equal to log base 3 of 1 minus x. Sorry, I have to keep turning around and see what the problems are. Haven't memorized them yet. Okay, so property of equality, bases are the same, interior must be equal to each other, so we have 7 minus x squared must equal 1 minus x. Again, we have a quadratic equation to solve. I'm going to move this over so I can have a positive x squared. So 0 equals positive x squared minus x, subtract the 7, and you get minus 6. Factors of negative 6 that add up to negative 1. So that'll be x minus 3 and x plus 2. So we get x equals 3 and negative 2. And now we need to check to see that both of these are in fact solutions. Okay. So I'm going to go ahead and do that check. I'm plugging into the two interior expressions. So I'm looking at 7 minus x squared. I'm looking at 1 minus x. Okay. Let's plug in 3 first. So 7 minus 3 squared, well, that comes out to negative 2. I don't even need to check the other one, although it'll give me the same result. This cannot be a solution because it gives us a negative inside of a logarithm, and that's a domain restriction for a logarithm. We can't have any negatives inside of the log, okay? So 3 does not work. The question is, does negative 2 work, or is this a no solution problem? So now if I try plugging in negative 2, I'm going to get 7 minus negative 2 squared, which is really just 7 minus 4. That's 3. That's okay. And when I plug it into 1 minus x, I get 1 minus negative 2, which is also 3. So x equals negative 2 is a solution, but x equals 3 is not. So you can write your solution set like this, with a line drawn through that, or you can write that x is just equal to negative 2. But I should see that you have 3 as a potential solution, and that you proved somewhere that it doesn't actually work out. Okay? So there's number 16. On to number 17. All right, this one's going to be a little bit different. Let's see if you can figure out how it's different. All right? So problem number 17. Almost there, guys. 3 more to go. Number 17. We have log base 9 of 3 is equal to log base 11 of 121 to the x power. Oh boy. So what's the issue? Why does this not look like the other ones we've done so far? The issue here is we don't have the same base. So we can't just do 3 equals 121 to the x. We can't just do the property of equality. But we can still solve this because there's a relationship between 9 and 3. We can figure out the value of this using the inverse properties that we talked about. And a similar thing will happen right here. Okay? So let's start working through that. So this is log base 9. I need to rewrite 3 as 9 to a power. Okay? Now we know the square root of 9 is 3, so this is 9 to the 1/2 power. Okay? So that means that this side, since I could make them both a 9 by making it 9 to the 1/2 is 3, this is really just 1/2 is equal to. Alright? We're going to do something similar on the other side. Okay? Here, I have log base 11, so I need to rewrite 121 as 11 to a power. Well, 11 squared is 121. And then power to a power, this is really log base 11 of 11 to the 2x, because power to a power, I can multiply those two exponents to get 2x. And now log base 11 of 11, those cancel out, and left with just a 2x. So this equation required a completely different approach, but we can still solve it because now we just have 1/2 is equal to 2x. So to solve that, I'm going to divide both sides by 2, or multiply by 1/2 to cancel off the 2 there, multiply by 1/2 here. So I get 1/4 is equal to x. Okay? And I just need to go back and double check and make sure that this is in fact going to not give me just a positive on the inside and not a negative. Okay? There was no variable on this side, so I don't need to check this. This was just a numerical value. But over here there's a variable. So 121 to the 1/4 power, that just means the 4th root of 121, but that's a positive value. So this is all set. So this is in fact our final answer. It does not give us a negative on the inside of the logarithm. Okay? We just have 2 problems left, all right? This one's going to go back to the same base, so we can use that property of equality. Okay, so number 18. Log base 2 of x minus 3 is equal to log base 2 of 2x plus 5. So property of equality tells us that we can just set the insides equal to one another. So we're really just solving x minus 3 is equal to 2x plus 5. That one's nice and easy. It's just linear. Okay, so subtract x. We get x plus 5 is equal to negative 3. Subtract the 5 and we get negative 8 is equal to x. And now we just need to make sure that we don't get a negative on the inside. Check for extraneous solutions. So I'm looking at the insides for x minus 3 and 2x plus 5. And when I plug negative 8 minus 3, that's negative 11. That's a no-no. So I don't even need to plug it into the other one. This is not going to work. Okay? So this is not actually a solution. Even though we could solve for it, it doesn't work because it's going to give me a negative inside the logarithm. It'll give me a negative inside the other logarithm too. So then what's the solution? There isn't one. This is a no solution problem. And just like many other types of equations that we have looked at, logarithmic equations can have no solution. It could be that maybe you actually can't solve it, or you get a solution and then it gives you a domain restriction. Okay? We have just one problem left to do, guys. Here we go. Problem number 19. I know this was a long lesson. You're all troopers for getting through it. Last one. And we'll call it a day. All right, problem number 19. Log base 4 of 4 to the 2x minus 7 is equal to negative 4. All right. Now this does not have a log equal to a log, so we're not using the property of equality. So we are going to need to use that inverse property again here. But the good news is we already have the bases matching. So because it's log base 4 of 4 to an exponent, it's really just the exponent, 2x minus 7, is equal to the outside, negative 4. Okay? Move that negative 7 over and you get 2x is equal to 3. So we get x equals 3/2. And again, we just need to make sure that that is not going to give us a negative inside. Okay? So we're plugging in the 3/2 into this piece right here because that's the inside of the logarithm. So we're doing 4 to the 2 times 3/2 minus 7. So 2 times 3/2 is 3. 3 minus 7, 4 to the negative 4. Negative exponent means just put it in the denominator. 4 to the 4th power, that's 256. But that's not even really important. At this point, we can see we're not going to get a negative value out of this. We're going to get a decimal value, but not a negative value. So this is, in fact, a solution. All right, guys, we did it. We've gone through the property of equality and solving. We've looked at the parent function graph. We've looked at properties, proving that they're inverses between exponentials and logs. We've done a lot of stuff. All right, call it a day. Good luck with your homework.